Okay, so here we have a cubical box. You know, all the sides are A, length A. 6 metal plates insulated from each other. Okay, so they're not conducting towards each other. The left wall is located at minus A over 2. The right wall at A over 2. Both left and right walls are held at a constant potential, V0. All the other 4 walls are grounded, up, below, top, bottom, front, back, meaning V0 is 0, or V equals 0, right? Right, and the cube runs from 0 down below to A in the Z, x equals 0 to x equals A, but then in the Y it goes from minus A over 2 to A over 2. Question says this might make the math a little easier. And we need to find the potential everywhere inside the box. Now here you could see that the potential will vary in every direction, along the x, along the y, and along the z. So this is a 3-dimensional problem. So this is a 3-dimensional problem. So we're going to be solving Laplace's equation, d squared v, or Laplacian squared v, to equal 0, which makes d squared v over dx squared plus d squared v over dy squared plus d squared v over dz squared equals 0, right? And we're going to solve this using separation of variables. So let's actually, so this is kind of like the topic of what we're gonna do, yeah? Separation of variables. This is an partial differential equation. Set 2 equal to 0. So you assume solutions of the form, yeah, v as a function of x, y, z. This is the method of separation of variables. Some function of x, call it big X, times some function of y, call it big Y, times some function of z, small z, call it big Z. Alrighty? Say that again? The reason we can do that is because if you recast, if you remember Poisson's equation, if you were to take the Laplacian of the potential, you get the Laplacian of the potential to equal 1 minus 1 over epsilon times rho, right? Well, inside our region there is no, this is the surface charge density, there's no charge, so rho is 0, so this guy is 0, and that's why Laplace's equation becomes 0. So with the appropriate boundary conditions, right, I mean this equation is identical to the the integral form of the potential, from which if you were to take the Laplacian, you will get this. You're just recasting the problem in the differential form. This is Poisson's equation, or Poisson, whatever his name is. Yeah? This is Laplacian squared minus 1 over epsilon rho. Yeah? Now, of course, if rho is equal to 0 everywhere, right, then V equals 0, and there's not much to say. I'm talking about, I mean, there could be plenty of charge elsewhere. But we are focusing our attention to places where there's no charge, and in that case, Poisson's equation reduces to Laplace's equation, in which if you write in the Cartesian coordinates will get you this. We'll get to the spherical coordinates later. That's for spherical shapes, and cylindrical coordinates for cylindrical shapes. But in a box, you know, it's convenient to use rectangular coordinates, yeah. And so that's why we said this equals 0. So, you know, this is confining our problem to places where the charge is non-existent.
Yeah, outside the charge distribution.
Yeah. So with separation of variables, if you do that, and we said that you differentiate this, so you take dv over dx, and y and z are independent of x, so this will get you just dx over d small x, y function of y, and z function of z. And if you do it again, d squared v over dx squared, you will get d squared x over dx squared, and again both of these are independent of x, y, z, right? Let me take this a little bit to the left. And so if I do this same exact thing again for the y, I would get d squared y, d squared v, sorry, over dy squared equals d squared equals x is independent of y, so x stays x. This is d squared y over dx squared, dy squared, and z is independent of y. And I do it again. I differentiate with respect to z twice, dz squared. X is independent of z, y is independent of z, and I get dz, this is y, d squared z over dz squared. Okay, and now I will take this and I will plug them here. So I will get, I will plug them into the differential equation, Laplace's. So we will get, if I do that, I will get, the first one is d squared x over dx squared yz. I'll drop the small x's, y's, and z's just to avoid clutter, plus the second one, x d squared y over dy squared z, plus xy d squared z over d squared equals 0. And now if you divide this entire equation, okay, if I divide this entire equation by x, y, z, so divide through x, y, z, which is v, right? So divide this whole thing by v. I will get, so x, y, z, so the y, z cancels out, and I will have left 1 over x d squared x over dx squared. Y and z, x and z cancel, so I will have 1 over y d squared y over dy squared, and x and y cancel, and I will have left 1 over z d squared z over dz squared equals 0. That's after I divide this by x, y, z. And yeah, so look, you can see here the first one is a function of x alone, the second one is a function of y alone, and the third one is a function of z alone, right? And the three add up to 0. And the only way that this can happen is if each one of these terms is constant, such that if this is c1 and this is c2 and this is c3, they would have to add up to 0. And now what remains to be determined is what is it that I do assign to each one of these differential equations. according to the boundary conditions. So let's write down the boundary conditions, then we will come back to this, to what each one of those can and will be. So we'll come back. So so our boundary conditions. So let's write down the boundary conditions. Yeah. So the boundary conditions. Right. Well, with the boundary conditions, we have, let's just look at the figure. We have v, so they're grounded on the xy plane, correct? So that's what, when if we're grounding on, yeah, so exactly, yeah. Okay, so we have when let's be a little bit more specific here. So when z when x equals a, right? So v equals 0 when x equals a, and v equals 0 when x equals so this is a, so 0, right, in the zy plane. So this is number 1, this is number 2. Okay, what else we have? Well, we know we need 6 boundary conditions, because this is this is second order differential equations, and there's 3 unknowns, x, y, and z. So each one will have potentially two coefficients. So we know we need 6 boundary conditions. So the third boundary condition, we know that bottom, and so the bottom is where z is 0, right? V is 0, and where z is a, v is 0. So the fourth one is v equals 0 when z equals a. Okay, and then the last one, or the one before the last one, we have y is a over 2. That's when v is v0, right? When y equals a over 2. And the last one, the sixth one, is v equal also v0 when y is minus a over 2. Okay, so we have 6 boundary conditions, right? We have 6 boundary conditions to play with here. And so now the question becomes, how will we choose those C's, right? The C1, C2, C3 on top. And so let's take a look. Any ideas here? I'll let you guess. Well, look, I mean, we know, if you look at the boundary conditions, you know that the potential has to go to 0 on the bounds for z and x, which means the terms relating to x and z have to be sines and cosines, have to be trig functions, have to be sinusoidal waves, because this is the only way you could fit them to 0 at those boundaries. Exponentials can't. There's 2 choices. You have exponentials, you have sines and cosines, and since those are 0, you would want the x and z term. So because of this, you would label this, right, minus k squared, for example. Yeah, and so that it can go to sines. I'll show you in a second that it does, and you can label this minus l squared. And if that's the case, if these have to add up to 0, then C3 will just have to be k squared plus l squared. You'll see in a second why I chose k squared instead of k and l squared instead of l. So yeah, so now I'm gonna go to my x equation. So let's start with the x equation. So 1 over x d squared x over what was it, dx squared equals, we assigned that minus k squared, yeah? And the reason we said minus k squared, because this will turn out to be sines and cosines, because multiply both sides by x and then move it to the left. This is big X, yeah, plus k squared x equals 0. This is a second order homogeneous linear differential equation. Find the auxiliary solution. Remember these basic differential equation class. So your characteristic equation or auxiliary equation, you assume solutions of y equals e to the mx, you plug it in, take derivatives, plug it in. So I'm skipping those, you know, in between steps, and you get, if you do that, you will get auxiliary equation. You will get m squared, right, plus k squared equals 0. So that means m squared equals minus k squared, and if you take the square root, you get plus or minus ki. Complex exponentials turn into sine and cosine, so I'll skip those steps, and this takes you directly to x equal a, right, cosine. Oh, and the reason I chose k squared not k, because look, I just don't want to involve myself with square roots at this point, so it can conveniently come out to k instead of square root k. And the reason I chose the negative k squared, because I knew this would give me sines and cosines in which I can fit into my boundary conditions relating to x equals 0 and x equals k. So this becomes a cosine kx plus b sine kx. Okay, this is my first one. Let's box it. Okay, moving on to the second one, the y equation. We said we're going to call that, for the same exact reasons we've discussed, minus L squared, because we can also fit it into, oh wait, we switched those. This is the, we said that the z was the minus L squared, right? We discussed it correctly, I just put it in the wrong place. So minus L squared, which will make this minus k squared minus L, plus k squared plus L squared, because they have to add up to 0. So the z, if I get sines and cosines, I have 0 potential on the boundaries. I can fit it into my boundary condition. And so, okay, let's solve the z one since it's similar. The z now, so I have 1 over z d where are we? Yeah, so 1 over z d squared z over dz squared equals, we said, minus L squared. And you follow the same exact steps for the one for the x one. We will get d squared z over dz squared plus L squared z equals 0. Second order auxiliary equation. You will get r squared plus L squared r, or L squared, equals 0, which makes r equals plus or minus Li, identical to the, you know, x equation, and we will get z to equal c cosine L z plus d sine Lz. Okay, here we go. That's our z1. Okay, now let's go to the last guy. The last guy, which is the y equation, which will be slightly different because now, you know, we have a k squared plus L squared. So if we go to the y equation, so this was the x equation, this was the y equation, and now, or sorry, this was the z equation, and now we're going to do the y equation. Let's do it. We have 1 over y d squared y over dy squared equals, we said they have to add up to 0, so this is just k squared plus l squared, yeah, which is positive. Separate the variables, same as before. You get d squared y over dy squared equals k squared plus l squared, which has to be a positive number now, times y. Move it to the left, so you get d squared y over dy squared minus k squared plus l squared y equals 0. Second order, non-homogeneous, homogeneous, linear. So auxiliary equation or characteristic equation, that will get you r squared minus k squared plus l squared equals 0. So r is plus or minus square root k squared plus l squared. Okay, so these are exponentials because you got a positive answer. So here we will get exponential terms. So y of y will have to equal, so we've used a, b, c, d. Let's call this e, exponential of k squared plus l squared y, right, plus def f e to the minus square root k squared plus l squared y. And this is my y equation. Now notice on the boundaries here, my initial conditions are for the y are different. Yeah, I have v0 and v0, so I could fit exponentials to be constants at the boundaries, but I can't fit them to be 0. You understand? So this is fine. This makes sense. Okay. Now what's our v? So our v is x times y times z. So I'm gonna multiply all these three. So we have v x y z equals x times y times z. So x turned out to be a cosine kx plus b sine kx. Yeah. You know, I could if I want, like I did before on the 2D one, I could impose my boundary conditions to each one separately for the same exact argument I showed you before. They are independent of each other in a sense, right? So yeah, so why don't we let me see, let's write it out. So a cosine kx, and then here we have d cosine, right? I called it cosine or sine? Yeah, cosine lz plus de cosine sine lz, and then the last term is e to the k squared plus l squared y plus f e to the minus k squared plus l squared y. Okay, good. So now let's start with the boundary conditions one by one. So we know the first boundary condition tells you that, let's start with the second one, easier. V equals 0 at x equals 0. V equals 0, so I'm going to start with the second boundary condition. The second boundary condition, V equals 0 at x equals 0. Now, those are unaffected, right? You plug in 0, you're going to get 0 equals a cosine 0 is a, cosine 0 is 1, the sine term goes away, times all this, right? Now, it's either the right hand side is 0 or a is 0. So that tells me a is 0. Okay, let's go to boundary condition number 2. Number 2 says that v equals 0 when x equals a, wasn't it? Again, the second two terms are unaffected because they're functions of L and Z, yeah? And right? So the first one has to be 0 for this to work. So 0 equals 0, this is, right? This is when x equals a, so this guy is gone here. So this is b sine kx. And then the rest don't matter because we said those won't be zeros. The exponentials can certainly not be zeros. So that means either the b is 0, which would be trivial. We're not looking for that. Or sine kx equal to 0, which would make kx to be, what are the angles whose sine are 0? Pi, 2 pi, 3 pi, 0, etc. So all the multiples of pi, which makes k equals n pi over, sorry, this is a, right? I'm supposed to plug in a here. So ka equals n pi, so k equals n pi over a. There we go. So we've determined what k is. Yeah, and okay, so this boundary condition solved for k. A is 0. Okay, let's go to the third boundary condition, and that will be for the z. Let's knock the z's out. So v equals 0 when z equals 0. This was boundary condition 1, by the way. So 3. So v equals 0 when z equals 0. Just go to the z term, and we will get 0 equals cosine d cosine 0, that's d, and sine 0 is 0, so d is 0. Okay, interesting. So that means this guy is out of the picture here, right? And the fourth boundary condition says that v equals 0 when z equals a. Yeah? Again, let's focus on the z term, the one in the middle. D is gone, so we have e sine LA, right, equal 0. Either e equals 0, which would be trivial, that's not what we're looking for, or sine LA would be 0, right? And in this case, what would L be? This will give us our L to be m pi, same thing, multiples of pi, but we'll call it m since we call the kn. They don't have to be the same, so we'll leave it general. So L is m pi over a. Okay, so far we've determined our k, L. We knocked out a and d. They all went to 0. Okay. And what do we have so far? Let's go to the fourth boundary condition, or sorry, the fifth boundary condition. V equal v0 when a is when y is a over 2 and minus a over 2. Okay, let's see. Okay, let's write out what, so now the y term, we know what k and l are, yeah. Let's write that out. So far we know that v x, y, z, right? A is gone. I can absorb the b and the e. B, D, E, oops, this is supposed to be F and G here, right? I can't use the same. Okay, F and G, yeah? F and G. Let me do this. Okay, F, call this G, or whatever. If I switch them, G, F. Yeah? Okay, so now I could absorb my sine terms together and into one coefficient, so right, and then that one, so these two guys, I can lump them into one coefficient, and since they're multiplying these two guys, all I have left are, I could absorb the B and the E into G and F, right? So I have two coefficients left. So let's just call them C and D, right? So what we have left is C sine kx, right? Cosine kx, right? Was it cosine? No, sine. They're both sines. Sine lx. And then what was the last one? The last one was okay. And now here I could have my coefficients. So I have let's just use C and D. So C. So those are different C's now. Okay, not the one I used. Actually, let's just stick with G and F. So G. So I'm absorbing the coefficients for the B and the E into G and F. So G E into L squared K squared plus L squared times Y plus F E to the minus K squared plus L squared times Y. Now keep in mind we've determined those K and L, but I just didn't write them so I don't clutter the math here. Okay, what was my last boundary condition? Last two. Number 5 said, so now I'm moving to boundary condition number 5. It said V equals 0, V0 at A over 2, when Y equals A over 2. So then V x A over 2 Z. So I can plug in A over 2 for Y. So I will get sine kx sine LZ, right? G E to K squared plus L squared times A over 2 plus F E to the minus K squared plus L squared times A over 2. And then the last boundary condition was at negative A over 2, right? It's V0. So this guy I could set it equal V0 here, yeah? So this is equal V0, and likewise the fifth boundary condition, the sixth boundary condition at minus A over 2, right? Wait, we could let's see here if we could solve for because I only have two unknowns in this equation, right? So I can solve for one in terms of the other. And if we do that, let me see. Well, these two, oh yeah, but they have different coefficients. Hold on. Z, yeah, right. Yeah, we forgot to do one thing, Ben. Which is okay, we could do it now, it's not that big of a deal. We know, okay, look at this exponential. If y goes to if y goes to infinity, the potential goes to infinity, right? If y goes to infinity, the potential goes to infinity. You agree? But that's not what we want, is it? That's not what we want. So because we want the potential to be confined to V0 on the boundaries. So if you were to no, because you see, when we plug this in, this is z, right? You're gonna get also v0 equal sine kx sine lz, right? G e. Now these will switch, so you're gonna get minus k squared plus a squared a over 2. Is it a over 2? Wait. Where did I get the a over 2? Oh yeah, because it's a over 2, yeah. Plus f e to the k squared plus l squared and minus minus, right? Becomes plus a over 2. Okay, now you could see that these are the same. Yeah, if you divide, these go away, and so you get v. So divide both of these equations, you get 1 equals g e to the you know what, I don't want to keep let's just label, tell you what, let's do a little bit of simplification here. Why don't we label this to be alpha, so we don't have to keep rewriting it? Yeah, or even let's include it with the 2. So this guy here, let's call it alpha. So if we divide these two equations, these two boundary conditions, we should get 1 equals alpha, right? G alpha, G e to the alpha a plus f e to the minus alpha a over g e to the minus alpha a plus f e to the minus to the plus alpha a. Okay, cross multiply, you're gonna get g, basically they're equal, yeah? G e to the alpha a plus f e to the minus alpha a has to equal g e to the minus alpha a plus f e to the alpha a. Now if those are the same coefficients, I mean the same exponentials, their coefficients have to be equal, and the same exact story here. This has to equal this, and therefore, so what these boundary conditions are telling us, that f has to equal g. So technically I have one boundary condition that is left to be determined, right? So f has to equal g. And so with that said, go back to our potential and pull that coefficient out. So we have vxyz. So I'm gonna write it with the same color. I'm redoing this guy here. So vxyz has to equal. So now I can lump these two into one coefficient, and I'm gonna call it c, right? And sine kx, right? Sine lx, I'll put those l's in case later, so we don't clutter this now. E to the alpha over 2a plus e to the minus alpha over 2 wait, why no, I can't use the alpha, because alpha was something else. So this is k squared plus l squared y. Oh wait, I also forgot the square root of these, yeah? There's a square root here. Not that it's gonna matter, but I did. There's a square root here. Square root, right? Because when we solved for this, it was, yeah, there was a square root. Okay, so minus e, so we have k squared plus l squared y, k squared plus l squared the y is outside the root, and minus k squared plus l squared y. Okay, now we're gonna make the same exact argument we've made before. Here, buried inside of this, we have, remember, k turned out to be n pi over a, and l turned out to be m pi over a, right? And there's an infinite number of these. And this becomes n pi over a squared, right? Plus m pi over a squared square root plus e to the minus n pi over a squared plus m pi over a squared square root, right? y. Okay, so look, so we know that if this one is a solution, the top one, so is any constant multiple of it, and therefore by superposition we know that the sum, right, is also a solution. The sum has to also be a solution. So that means I have a double summation, because I have, two varying indices here, the n and the m, one for each. Yeah, so this is from n equals 1 to infinity, m equals 1 to infinity, and then I have my coefficient c. Let me move these backwards a little bit. And then I have my coefficient c and m, all that, right? And now the question becomes, how do I get those coefficients out of that series and evaluate them? How do I find what these c's and m's are? And I do that by imposing one of the last two boundary conditions. They both told us that the coefficients have to be the same, and the other one, we could use either one. So if I impose my boundary condition number 6, right? If I impose my boundary condition number 6, what did that say? That said that v equal v0 when y was what? A over 2? Am I right? Was it a over 2?
Yes.
Yeah, a over 2 or negative a over 2. Okay, let's just do a over 2. So plug it in, and we will get v0 on the left equals double summation n equals 1 to infinity, m equals 1 to infinity, c n m sine n pi over a sine m pi over a, right? And now on these exponentials, plug in a over 2. So we're gonna get e. How about we just call this whole thing here alpha, or beta, so we don't have to keep writing it, because this is gonna be a lot of writing here. So let me just call this alpha beta, and so is the other one. So this is beta, right, including the square root, and this is what, a over 2. A over 2 plus e to the minus beta a over 2, right? Okay, and what is this here? This is cosine hyperbolic beta a over 2 times 2. So I could replace this with the cosine hyperbolic beta a over 2, right? This is a constant. Okay, now how do we get our coefficients? That's the trick. Well, if you remember, we use Fourier transform. This is nothing but the sine Fourier transform, and we could use the Fourier transform trick, yeah. so after we did the most general linear combination in a double sum, right? What we could do now is we could multiply both sides by we have two signs here, correct? Yeah, we could multiply each, so we have two sign transforms. We could multiply each one by its corresponding m pi over a sine term and integrate both sides. Yeah. And so if we do that, so let's do that. So I'll move this cosine hyperbolic to the left just to make it less clutter here. Oh, and there's a 2 here because this is technically over 2. Yeah. So we will get v0 over 2 cosine hyperbolic. Now remember, all this is a constant times beta a over 2, right? Equals this double summation n equals 1 to infinity, m equals 1 to infinity, yeah, c n m sine n pi over a sine m pi over a. Okay, so these are two sine transforms. So what I'm gonna do now, let me rewrite this. v0 over 2 cosine hyperbolic beta a over 2 equals some double sum c and m, n equals 1 to infinity, m equals 1 to infinity. And what I'm gonna do, the first sign, I can expand this in a Fourier series, and I'm gonna multiply it by sine m pi over a, right? And I'm gonna integrate this from 0 to a, right? Wait, where is my oh, I forgot the x, yeah? Wait, this is oops, all kinds of mistakes here. This is LZ, so there's an x here and there's a z here, yeah? There's an x here and there's a z here. Okay, there's an x here and there's a z here. Okay, so has to be a variable, yeah? So this first one is the x, so we multiply it by an x, right? Integrate dx. Now why am I doing this? I'm doing this because I know with the Fourier trick that this integral will be 0 for all the terms except when n equals m. So that would knock off all my terms in the series except where they're equal. So save 1, everything else will be 0. Yeah, okay, I won't have room here, so times, let me continue below it. So this is all inside the summation, by the way. So now I'm going to deal with my second term. Yeah, sine m pi over a z, right? And I'm going to multiply this by sine n pi, right? I could do n, yeah, that's fine, or m prime, whatever. I could have you know what, let's just to avoid any confusion, let's do n prime on this, yeah, and let's do m prime on this. So m prime pi over a z, and I will integrate this from 0 to a dz. And likewise, this will knock out all the terms where m prime doesn't equal m, and we'll only have one term left when they're the same. Okay, now wait, but I have to do the same exact thing to the left hand side, which I didn't do yet. So technically I'm supposed to multiply the left hand side by and wait, if this is, oh yeah, this is, they're both over a, yeah, because it's a square. So so I'm supposed to multiply this side also by sine, what was it, n prime pi over ax, right? No more room here. And then dx on this one. And then another term, so times sine m prime pi over ax z. This is a z dz, and each one of these is, this is a double integral going from 0 to a. Yeah. So technically what I have, maybe it'll become clear now on the second step. So these are all together here. This is the left hand side of the equation, and this whole thing here is the right hand side of the equation. Okay, let's integrate. So v0 over 2 cosine hyperbolic, so let's call this the left hand side, and let's call this the right hand side, and we'll do them separately. So if we were to take the left hand side, right, what's this double integral? So this is v0 over 2 cosine hyperbolic ba over 2. Remember, the objective is to find c and m. So we have sine n prime pi x over a, right, dx, because because we did this on the right hand side, so we have to do it on the left. 0 to a, and then we have 0 to a sine m prime pi over a z dz. Okay, and what do we get here? We get v0 to cosine hyperbolic ba over 2, beta a over 2. Okay, what's sine? Negative cosine, so minus cosine n prime pi x over a, and then chain rule that, so divide by n prime pi over a, or multiply by a n prime, right? So this is going from 0 to a, and multiply by the chain rule, which is the chain rule is a constant, so I don't need to put it inside the evaluation bracket. So this is a over n prime pi, a over n prime pi, yeah. And evaluate. Notice that the first integral is identical to the second integral. You just replace n prime with m prime, so I don't have to evaluate both of them. And if I plug in a, I will get, so let me lump all these constants on the left hand side. So we will get minus v0 a over 2 n prime pi cosine hyperbolic beta a over 2. Okay, if you plug in a will cancel out, and you get cosine n prime pi, minus, if you plug in 0, you get 1. Okay, what does this equal to? Well, if n prime is even, right? Remember, I only evaluated one integral here, but the second one will be identical. So I only did this, right? So this will equal, now if even multiples of pi will be 1, right? So I'll get 0. So if n is even, this whole thing will be 0 for n even. And if n is odd, it'll be minus 1 for the odd multiples of pi. Minus 1 will become minus 2, and there's a minus here. So you will get, and then, this becomes 2. It crosses out with that 2, and you will get v0a over this thing here paused, so let me open it back. It's not taking the pressure of all that math, right? Radiation pressure is getting high here, I guess. So this guy is minus 2 if n is odd, so this crosses out with this, the minus sign goes away, and we get v0a over n prime pi cosine hyperbolic beta a over 2. That's if n is odd. Which means the second term will be the same, correct? Oh, I shouldn't have involved the wait, I need to keep this outside the equation because this is the same as both of them. So without this, what did I get? Without this, I got this integral to be yeah, I should have left that outside here. Wait, let me fix this really quick. So keep that minus outside. So this is all multiplying, right? This is all multiplying. So I could switch the sign and absorb the minus sign n, right? And I will make this a over n prime pi. Okay, and this now would, yeah, if n is even, you would get 0, and if n is odd, you will get this, except that I have another term like this. So I'm gonna get minus v0a. So I will just write the result as if I have evaluated this, okay, because this is a z and it'll be the same thing. So because you're going from 0 to a, so you will get leave this 2 here, right? So if n is odd, here, let's rewrite the result. So if n is odd, we will get minus v0a over 2n pi cosine hyperbolic beta a over 2, right? And if n is odd, this will become minus 1, right? And there's a minus, so this becomes 1. So this is times 2 over 2a over n prime pi. Okay, so on the second guy, I will get 2a over m prime pi. So now the left-hand side will become, right, for this integral, minus v0a over 2n prime, this is n prime, pi cosine hyperbolic beta a over 2, right, times 2a, is it 2a? Yeah, 2a over n prime pi, and from the other one we will get 2a over m prime pi. You agree? M prime pi. I just, so this is assumed based on this answer. So I didn't do the whole thing. Yeah, and so okay, and so what we will get here is let's see, 4. Yeah. Okay, good. So so that's the left hand side. Let's simplify this. We will get v0a. So we have v0a. Wait, where did the v0a come from? Where did this a come from? I don't have an a here. How did I get this a? Oh yeah, I removed this a. So there shouldn't be an a here. So this a, I've already, you know, split them. Yeah. Okay. I already split them. So okay, so moving on. So then if we simplify, we will get this is the left hand side. Let's leave it as is, it's fine. Now let's go to the right hand side. So the right hand side should be slightly more, hopefully, straightforward. Let's see. So we said that according to Fourier trick, all these will be zeros except when n equals n prime equals then this whole thing will be what, 2 over a, right? I mean, you could integrate and find out it's sine squared, you know, integrated from 0 to a. This problem is getting already long, so I don't want to make it any longer. It is, I think, 2 over a. Let me just make sure, 1 second. Let me look at the integral of sine squared. This is because one mistake here and the entire answer would be wrong. Let's see. One moment. I'll actually do it on the calculator really quick. I'm doing it on the calculator. Yeah, you get a over 2. You get a. So you're gonna get. So all of them will go away. Yeah. And then you'll get a over 2 for. So we have, okay, so the right hand side becomes CNM times a over 2 for the first guy, but then you also have the same exact Fourier trick on the second guy on the right hand side, on this guy here. This will also get you a over 2, right, from 0 to a. So you get a over 2 times a over 2. You understand what I'm saying? Yeah, because the right hand side is basically the integral of this, n pi over a x dx from 0 to a. You could use, I mean, if you really want to see it, you could use the 1/2 trig identity, 1 minus cosine twice that, right, 2 n pi over a x dx. And so what's this? 1/2 x minus sine 2n pi over ax, and multiply or divide by the chain rule. So this is a over 2n pi, and evaluate from 0 to a. So so what do you get? 1/2 if you evaluate a minus, right, 2n pi. If you plug in a here, right, you get 2n pi. You get, this goes to 0, and if you plug in 0, 0 plus 0, yeah, so the only term that survives is the first one, a, and you have half outside, so you get a over 2. You see, that's what I'm saying. So each one of these turns out to be a over 2. Okay, good. So we confirmed it by doing it manually, in addition to the calculator. So yeah, so now that's it. It's almost there. So this has to equal this. The right hand side has to equal the left hand side, yeah, according to our equation. And now we can solve for the c's. So here we have CNM times a squared over 4 has to equal that whole thing, 4a squared over, yeah, over n. I'll use n and m instead of n prime, pi squared times v0 over 2n, right, 2n pi cosine hyperbolic beta a over 2. Okay, and then just simplify. So these two go away, and you get c and m to equal 16 v0 over we have pi squared. There's another pi, so what does that make it? N squared. I have a feeling I may have repeated one of these. Second. Oh yeah, I did. I repeated this. I already absorbed this there, yeah, because this is v0 over 2 cosine hyperbolic. Yeah, I did. So I don't need this. Do I? Yeah, we messed up here. So v0, because I separated them again. I combined them, then I separated them again. So because see, I have it here. So this is what 2 from 0 to a, and I put the minus sign outside, so this will be oh yeah, you see, if I put the minus sign outside, I don't need this minus sign, so this becomes minus, yeah, and this becomes minus 2 a over n prime pi. Okay, now it sounds good. So we were off by a minus sign and that extra n term there, so I don't need this here, yeah, and this becomes here a plus. Okay, good. So so now bringing this down, cn a squared over 4 equals 4a squared. We don't need, we just have 2 4a squared. We don't need this 2, so we have cosine hyperbolic and pi squared times m, yeah, so mn. Okay, good. So yeah, we've come a long way. So cnm then equal to 16 v0 over pi squared. Bingo. Pi squared m n cosine hyperbolic. Now what's beta? Beta, if you remember, what I called beta was this whole square root thing, yeah, n pi over a squared n pi over a squared was, let me see, yeah, with the square root plus m pi over a squared. There we go, and this is really what we spent most of our time going after. What are these coefficients? So now you can see that for every n and m, you're gonna get a different coefficient. And now finally we can write out what v is in terms of these n and m's. So finally we have v as a function of x, y, z, right? So just plug this these coefficients into the double summation here, right? Into where's the equation here? Into this equation, yeah. So here, should we just take this final step and just drag it down there? So this is my let's copy this and put it here. It's not reacting well to that copying process because it's a long one, yeah. It's not liking that at all. Okay, it's fine. Let me a second. This thing quit on me. Okay, perfect. So so this is our potential. Just replace that with you know, with CNM. So we get V x y z. Now that we've determined what these CNMs are, everything that doesn't depend on NM, I can take it outside. So 16. Let's hope I can fit this whole thing here. Yeah. So 16 V0 over pi squared. This is also a constant. I can leave it out. Oh, actually, it depends on n and m. No, I have to take it inside. So double summation, right? n equals 1. Oh, remember, only the odd ones survived. So n equals 1, 3, 5, because all the even ones went to 0, yeah? Etc. And same thing for m. 1, 3, 5, etc. Yeah? And c and m turned, so this is 1 over mn. And there's a cosine hyperbolic here. So cosine hyperbolic n pi over a squared plus m pi over a squared, and there's a square root. Yeah? And then I also have, of course, the sine terms. So let's put the sine terms here, otherwise we're not going to be able to fit it. Sine. So I'm done with the CNM, that's CNM. So I have a couple of sines. So n pi over ax, right? Sine m pi over az, and then I have my y terms as exponentials, so times e to the n pi over a squared plus m pi over a squared square root y plus e. I could write this actually as yeah, why don't we do that? Let's write this as a cosine hyperbolic. Yeah, so it'll be 2, this whole term will be 2 times cosine hyperbolic the exponent, because it's e to the x, e to the alpha plus e to the minus alpha. That gets you 2 cosine hyperbolic alpha. So so I can bring, so this becomes 2 times, so this 2 I can multiply it with the 16 here and make this a 32, and then I can rewrite this term as cosine hyperbolic n pi over a squared plus m pi over a squared square root y, and this whole term is inside the cosine hyperbolic. This is the final solution, finally, for our for the potential in that cube. This is to infinity, this is to infinity. Yep, this is called separation of variables. A bit lengthy, especially in 3D. So you know, it does get here a bit involved.